Okay, let's get started. As I had mentioned at the beginning of last week, we were going to be spending a few weeks working on a series of topics that are related to dealing with rational expressions. So last week, we did a review of basic stuff you should have known from Algebra 1, Algebra 2. We looked at something called the difference quotient, which is the small part of a bigger calculus formula. We looked at how this stuff appears in a more complicated version in messy calculus-related fractions. How does it appear on the SATs? Okay, today we're back to another calculus application where it's easier to do calculus sometimes on smaller, simpler parts rather than a bigger, messier whole. So for this pre-example right here, one thing that we know how to do is if we're given two smaller individual fractions, can we add them up to get a more complicated single fraction? What we're going to be doing today, tomorrow, and through Thursday of this week is going to be, instead of starting with two smaller fractions and adding to get one bigger one, we're going to start with one bigger one and break it up into these two smaller individual fractions. Okay, the overall plan of attack is today we're going to do the first four from this handout. Tomorrow we're going to do the second four from this handout. Wednesday will be a review day. Thursday will be the quiz. The quiz will be in class. Those of you at home, obviously you're taking it at home, but it'll be during regular class time. Those of you in class, same story as the last quiz. You can bring your own device if you want. Other than that, the Chromebooks will be here. All right, so that's the where we are, where we're going. Oh, and this is in section 7.4 of your textbook. As I had mentioned at the beginning of last week, the topics we're going to be working on are kind of scattered throughout the textbook. They used to be more localized in an older edition of the textbook, but it was like corporate rated and split up among different chapters. But I still like doing this as it's kind of old single chapter it used to be back in the day. All right, so starting with number one. If the denominator of your fraction of interest is not factored, factored, then you want to get it factored. So this is going to factor into x minus 3, x plus 2. Okay, the pattern for this factoring is going to determine the pattern for your split. This here, we're going to classify as distinct linears. Distinct, meaning different. Linear, each one of those is to the first power. For distinct linears, what's going to happen is each one of those binomials is going to become the bottom, bless you, of its own fraction. And what we're going to have is a single variable we're going to solve for up top here, single variable we're going to solve for up top here. The convention with this is to use capital letters. I'm not sure why they decided to go with capital letters as opposed to small letters. I was not invited to that meeting when they made that decision, but capital letters is what they roll with. All right, next move is we're going to multiply through by the common denominator. For the types of problems we're going to be doing in here, that original denominator that we split it up, that's got split up, that's going to be the common denominator. So this times that far left fraction, both binomials cancel with both binomials, and you're left with x plus 7. For the middle fraction, x minus 3's cancel. You're left with the a, x plus 2. And on the far right, the x plus 2's cancel, and you're left with b, x minus 3. Now, our goal is not solving for x. Our goal is to solve for a and b. We want to know what the tops of these fractions need to be such that when these get added together, it produces that end result. There are a couple main strategies that we're going to be learning. The first strategy that we're going to be using for the first three problems, I call the happy value method. Okay, the book calls it something else that's more politically correct than the happy value method. I don't remember what it is. It's in section 7.4 if you want to know its name. It's the procedure that's important. So what we're going to do is pick a convenient value of x that we could plug in that will allow us to solve for a or b. The convenient values tend to be, well, what makes those things 0? Because then stuff drops out. So if we let x be -2, this is going to drop out, and we can solve for b. So we're going to plug in -2 for x. That's gone. We get 5 is equal to -5b. B is -1. Okay, then the other convenient value to choose would be, well, what if x is 3? That'll cause this to drop out, and then we can solve for a. So we're going to let x equals 3. Oop, why'd I, hold on, let me get that a little bit clearer. What's grouped with what? So now we write our final answer. A is 2. So it's 2 over x minus 3 plus b is -1, -1 over x plus 2. All right, there's nothing magical or important about the fact that we had x minus 3 as the first denominator and x plus 2 as the second one. We could have set it up with those two things reversed, which would have led to -1 over x plus 2 over x minus 3. The other common variation, if it's plus or minus like that, very often I'll just make it a difference of those two fractions. So any of these would be acceptable final answers for our partial fraction decomposition. Go with number 1. Okay, for number 2, the bottom of the fraction is already factored. So we don't need to do any factoring there. Now, in many, probably most corners of the math world, we would consider the bottom of the fraction to be quadratic. In the partial fraction world, we're going to classify it as a repeat linear. If it's a quadratic that can be written as a linear times itself, then it falls under the repeat linear pattern. Okay, the way it works for repeat linears is you're going to have that thing to the first power, and then you're going to have that thing again to the second power. Now, why the first and why the second? The answer to the why falls under uses math that we really don't want to know about. For this particular little set of topics we're going to be doing this week, we don't really care why it works. We just have to know that this is what we do to get the final answer. We're just driving a car. We don't have to build it here. Now, if it's a linear, it's always a single variable on top for each one. So big picture recap, we want to take this fraction, write it as a sum or difference of smaller individual fractions. How this factors on the bottom determines how we split it. So distinct linears was the last example. Repeat linears is this example. Okay, regardless of how it got to here, the next move is we're multiplying through by the common denominator. So this times the far left, the x minus 5 to the second power cancel. For the middle fraction, that cancels with one of those, and it leaves you an a, x minus 5. And then for the far right, the x minus 5 quantity squares cancel, and it leaves us this. Good? All right, now, for the first example we did, we were able to find B without knowing what A was. We were able to find A without knowing what B was. We can independently find one without knowing the other. That's not always the case. What's going to happen here is if we plug in x is 5, that's going to drop out and we can solve for B. But we can't solve for A without knowing what the B is. Now, usually with these guys, you want to have a little bit of a plan of attack, especially since we're going to be learning a couple of different strategies. Before you just dive in and start doing stuff in a problem, you should try to think ahead, well, is what I'm going to do or want to do really going to work? Now, being this is only the second one you've ever seen your entire life, it's tough to have a good decision, but I want to start like building that thought process of how do you think your way through the problem. So if I do let x equals 5, I can solve for B. Once I know B and I plug in a number, there's only one variable left. I can absolutely be able to get to the final answer with that plan of attack. So x equals 5. 5 times 5 equals A. 5 minus 5 plus B. That's gone. B is 25. Okay, for the reason just explained, in order to move forward, we have to plug that 25 in for B. Now, with this happy value method, you can only use every happy value once. So we've already used 5. Now, we only have one variable to solve for. We can pick anything we want. If like 237 is your lucky number, you can plug in 237 and solve for A. We can pick anything we want for X other than 5. Pick something that's going to keep the math as simple as possible. 0 is always a good choice. If that's the case, 1 works pretty well most of the time. In this case, 6 works pretty clean too, because if you plug in 6, it just leaves 1A. So I'm going to go with X is equal to 6. If you want to pick something else, you can. I'd avoid the 237 number, but other than that, you should be good. What's up?
Is there a way to like double check these? Is there some?
Well, if you'd have to actually add them together to double check them, which I'm not going to do until we get through all the examples. If we have time, I'll check that last one just to like verify. But I want to make sure we get through the 4 examples.
For ones like this, you have to plug in something for x, or could you just solve for a? Because the x minus 5 can cancel out the other side, or is it just because that's not always going to be the case?
I think you might be thinking ahead to another strategy that we're going to get to that I'm going to show you with number 4. There's multiple ways to do this. I'm kind of just for now sticking to the one method of choosing the happy values. But I think you might be describing something else. Yes?
On a test or quiz for the happy values, is it going to affect our answers if we pick different ones compared to what you did to solve it?
No, it's going to be the same no matter what. And you might not even want to be using the happy value method once I show you other things.
Okay.
This is just one way to get the job done. Yes?
It's like 5 and the x minus 5 is the first power, and like the 25 with the x minus 5 squared. Is that
Now, that's an excellent observation that I don't recall ever being asked that before, but it was asked last period. And no, that's just a coincidence that it happens to be 525. Because with these first examples for today, I tried to pick like numerically simple ones. I have a feeling that maybe that's a byproduct of just being a very simple one, but in general, that's not always going to be true. Anything else before we go to number 3? All right, with number 3, what happens is we have a couple different things going on in the same denominator. So for number 3, we're going to need to factor out an x. That leaves x squared plus 2x plus 1. That trinomial factors into x plus 1, otherwise known as x plus 1 quantity squared. So number 3 is kind of a blend of numbers 1 and 2 in terms of what's going on. We have a distinct linear, the x, and we have a repeat linear, the x plus y to the second power. So for the distinct linear, that's going to be the bottom of its own fraction, single variable up top. For the repeat linear, we're going to need that thing to the first power, and then that thing again to the second power. Single variables on top. Now, if that happened to be the third power, we'd have another fraction. If it was to the fifth power, another one after that. You'd keep extending it out as many times as you need to hit that exponent. Regardless of what this split looks like, at the end of this step now, we're multiplying through by the common denominator. So on the far left, that cancels with that, and it leaves just the top. Okay, for the second fraction, the x's cancel, and it leaves you a x plus 1 quantity squared. For the third fraction, that cancels with one of those, and it leaves you a bx x plus 1. And then for the far right, the x plus 1 squareds cancel and leave you just cx. All right, so if you are going to do this by happy values, again, it's not your only option. It's just a strategy we're focusing on for the first few problems. Okay, how would this thing play out? Well, the first happy value to consider would be, well, what happens if you plug in -1 for x? So if you let x be -1, that drops out, we can solve for c. So plugging in -1 for x will allow us to get c. Okay, the next happy value would be, what if x is 0? If you plug in x is 0, that drops out, we could solve for a. Now, once we have a and c, if we plug those in, then we could definitely get b. There's only one variable left. So that's going to be a plan of attack, not necessarily the only one, but one that will work well. I'm going to plug in -1 for x, that'll get me c. I'm going to plug 0 in for x, that will get me a. Once I know those two, I'll pick some other number to plug in and get the b value. Everybody okay with that? All right, so plugging in -1 for x. Gone. This is going to be 5 minus 20 plus 6. I do not want to know why I have that parenthesis there. So it's going to be negative 15 plus 6, negative 9. So C is 9. All right, so that takes care of the first thing I wanted to do. That's step 1 of my plan. Step 2 of my plan is I'm going to plug in 0 for x. So if I plug in 0 for x, I'm not even going to recopy all of this. That's gone. That's gone. We're left with just a 6 on the left-hand side. That's going to be a 0 plus 1 quantity squared, which is just ultimately going to be a. That's gone. That's gone. A is 6. Now, if you have trouble visualizing that with the mental math, you can plug it in everywhere. I mean, show whatever work you need to. But these problems are kind of long enough as it is. Look for nice little shortcuts like that to pay attention to. Yeah, because once, if it's this times this times this, once one of them is 0, the whole thing has to be 0. Now, we already decided that by this method, we're going to have to plug in A and C in order to get B. So we got 5x squared plus 20x plus 6. We now know A is 6. B is what we're looking for next, right? Yeah, so bx plus 1 plus 9x. All right, we've already used x is equal to negative 1. We've already used x is equal to 0. So we need to pick a third x value to plug in. I would go with 1. You like something else, pick something else. So if you plug in x is 1, it's going to be 5 plus 20 plus 6. That works out pretty clean. 6 times 1 plus 1 squared. B times 1, 1 plus 1. And 9 times 1. Sorry, I left off the page. So now we can write the final answer. A is 6, so we have 6 over x. B is negative 1. And then C is 9. Yes.
So that negative one in the numerator is in the final answer. That'll, like, it's 6 over x minus, 1 over x was
Yep, that'll work. Either one is perfectly acceptable.
And like on the quiz, that'd be like indicated, like would you have to like match your work with that or?
Right. Well, being we're going to be doing this in Edulastic, this will be set up like it'll already give you like this. So you just have to make sure you type in like b is -1.
Oh, okay.
So it'll be like a fill in the box or whatever.
Yeah, it'd be the drag and drop or just to type in a number. So you'd have to drag and drop or type it in to match whatever, like, if that was already a minus, you'd have to put in a +1. If that's a plus, you have to put a -1. But I tried to keep it like relatively clean for the quiz so as that you're not getting the answer wrong because of that. And anything else before we go to number 4? All right, last example for today. Number 4. Top of the fraction, we're good. Bottom of the fraction, we need to take out an x. Okay, so here for the x, we have a distinct linear. This is the first time now that we have a true quadratic. This is a quadratic that cannot be written as a linear times itself. So for the distinct, it's not a plus. For the distinct linear, that's going to be the bottom of its own fraction. So it'll be an a over x. For a distinct quadratic, that'll be the bottom of its own fraction. But now if this is a quadratic, we have to have a linear up top. So what we're going to have is a bx plus c. So if there was another distinct quadratic, then we'd have a dx plus e. If there was a third distinct quadratic, you would probably want to find me and hurt me. But if it existed, then you'd have a, what would that be, an fx plus g, whatever follows, follows. So linears always have a single up top. The quadratics that are not repeat linears always have the binomial up top. So we're going to multiply through by x squared plus 4. This is still going to be the common denominator for the whole equation. So this times the far left denominator completely cancels. For the middle fraction, the x's cancel, and you're left with a x squared plus 4. And then for the right fraction, the x plus 4's cancel, and you're left with x bx plus c. Now, just thinking ahead, if we wanted to do happy values, how would this play out? Well, we could let x be 0. This would be gone, and we could solve for a. Even after we plug in for a, we're kind of running out of happy values because the only way that we could get this to cancel out to get something else would be if we introduce 2i. Imaginary numbers are not allowed here. So we're kind of having our happy values not be so happy here. So a completely different strategy that you can use is a grouping strategy. What you do by this strategy is you're going to multiply everything out on the right-hand side. And then you're going to look to see how things on the left group up with things on the right. So we're not doing anything with the left-hand side at this step. When we clear those parentheses, we're going to get ax squared plus 4a. When we clear the right, we're going to get bx squared plus cx. So here's our next plan of attack here. On the left, we have a 3x squared. On the right, we have an ax squared plus a bx squared. So if the stuff on the left has to line up with the stuff on the right, then a plus b must equal 3. Okay, that takes care of those guys. Now we have a 4x on the left. We have a cx on the right. C must be 4. And then lastly, we have a plus 4 plus 4a. That means a must be 1. So now that we know A is 1, we can go back to this one. B must be 2. And now we have our 3 values that we're looking for. All right, so writing our final answer, we have 1 over x plus b is 2, so 2x plus 4 over x squared plus 4. That's our final answer. Megan, is that what you were getting at? A little bit? Okay, yeah. I think you were kind of describing what just happened here when you asked that other question. Yes.
On the right, like for the numerator, 2x plus 4, you would never simplify that to like 2x plus 2 times x plus 2.
You could, but typically you don't. For what we're doing here, it would have no impact. If this were actually the smaller part of the calculus problem it came from, that would make it a little bit messier. It's usually better to leave it like that. Again, for the quiz, you'll just have to make sure that you line it up with the format that it's given to you. Yes? That's just the rule that's the rule for the split. That if this is a quadratic, that's what you have to put up top. It's just starting with, like if that was the first fraction, it would be an ax plus b. Whatever, just like roll with the pattern of whatever comes next. Yes?
Does 4a go with 4 because they like added them having x with them?
Well, that's a constant. That's a constant. As in like no x terms. Yes?
Could you split x squared plus 4 into x plus 2 and x minus 2? Or?
Now, that would be true if it was x squared minus 4. X squared plus 4 as is won't cancel. If that was an x squared minus 4, then we'd have 3 distinct linears, and it wouldn't be in the quadratic category. Yes?
Does it always follow like that format, the bx plus c? It's always like the next capital letter x plus c, that's for quadratic. Like it always
Yeah, well, you know it has to be a binomial because that's quadratic.
Yeah.
And then the letters you choose is whatever comes next.
Yeah. So it follows that same format.
Yep. All right, we're a little shorter on time than I thought we would be, but it's no big deal. Let me just check this one, and if there are more questions, I'll answer them. So if you wanted to check this answer to know whether it's correct or not, we'd actually add these 2 fractions together and see if it's got us back to the original. So the common denominator to add these would be x squared plus 4. Okay, that's the same. So the new thing is multiplying by x squared plus 4. 1 times x squared plus 4. X squared plus 4. That was already there. The new thing is multiplying by x. X times 2x plus 4. So the bottom is the bottom is the bottom. And we got to do this math across the top. That's 2x squared plus 4x. 2x squared, x squared, 4x plus 4. Hopefully that matches the original, or I'm not going to have time to fix this. Yes, we're good. All right, those of you at home, unfortunately, we ran a little bit long with these examples. I'm not going to really be able to address any significant questions. There should be time tomorrow if you do have any. Homework is posted in Google Classroom. You guys can leave Google Meet if you'd like. All right, this homework worksheet, there's 8 of these problems. I don't think you necessarily have to do all 8 for practice. If you feel you need to, go ahead. I would definitely try at least a couple of them that appear to be more complicated than what we did. To make sure you can do the next level of difficulty.
How do you feel about
So we're gonna find ways.
So you just
Ah.
The SAT math part was not as hard as I thought it was.
Okay.
Oh, that's good to hear.
Yeah.
Like, I was going through it and I'm like, did these get much harder?
Yeah, no, I took it in December, it wasn't like.
I'm
the
glad
math
when you
was
taught on Friday though, because the open-ended, at least on mine, were literally the exact
Yeah, I
questions.
was.
Really?
I'd like to say that I knew that was going to be the case, but I do not have that kind of power.
Like the open-ended was like the easy version.
It literally was.
Like
Yeah,
it never
like,
got
I
as
never-
complex as like that one worksheet. Kind of weird.
Well, that was an extreme worksheet.
Was it?
Yeah, they were like all high-end questions, so.
Because I, like, in December, like, we were looking at the worksheet then, and I was like, this is a lot harder than my SAT. So I was
one were
like,
easier than the one of those recent.
the what?
Like the ones in December SAT were even easier than the one on Saturday.
Yeah, that's what I thought too.
Yeah, the
I didn't
math
take
I did it really good last time.
I did so good on the last time.
Yeah.
The English I just like
So.
it was like the math I had to do.
I feel like
So I'm just hoping I did that.
Yeah.
I don't know, I thought it was hard.
Being in this class is a huge prep for SATs, because even the stuff that we do that's not an SAT topic, I teach it so as the thought process of how do you approach problems should carry over to the SATs.
all the, I had a couple like graphing questions and they were all the graph stuff that we like just learned.
Really?
The stat stuff too.
Yeah, like you guys I used my calculator and I wanted to put stats.
Oh my god, I used the calculator, because it was on the calculator section.
Yeah, I really-
Literally was just plugging stuff in and I was like, we just learned this.
That was my, these numbers seem big, let me just put it in stats so you get the equation for me.
I was literally kind of the stat throwing it and finding the little like, circle back to the calculator and I was like,
Instead of finding like the intercept, it was easier just to go on the calculator and just grab the points and find linear and find it that way.
Well, it's good that you recognized when to use it and knew how to use it. Because some people, they think that, well, I have a graphic calculator, I'll graph everything, and not really knowing like when's the time to use it and when's not. But if you have this skill to be able to get it in your calculator quickly,
I got a table with a bunch of numbers that says find like B of a linear line. I'm like, find this one, I feel it's easier to put it, a few numbers in stat and hit a button.
nice.
I did
I read it.
for
I tried to read
like
it.
3 or 4 questions were like that, and then like the last chunk of the open-ended, there were a bunch of kids that were like, I had no idea how to do that, and I was like, I learned that in math.
I feel like
The only thing that got me was like inequality. I don't remember them.
The inequalities, there was like a couple that I was kind of like, but like, I don't, for the, these are the open-ended, for the math, honestly, I don't think there were any that are actually like straight up like random number guess.
Everyone I got that at least two.
Actually, we've done almost nothing with inequalities this year. That was one of the things that was a COVID casualty.
Yeah.
So normally we would have done at least something with inequalities by now, but then again, we got to other things that maybe we wouldn't have gotten to.
It was like how many solutions does inequality have? I'm like, oh, I have no idea.
There were,
5-ish.
yeah.
Like, 1, 2, 5.
So much harder than the math though, like some of the questions were like, I was like, what is that? I was like, math, I was always able to work through, get like some
Those
letters.
colleges, I don't have the pets like that school, I can just focus on English.
Yeah.
And then the center is like.
Because English, I'm not gonna get better at unless I just.
It was like.
Math, I generally, I mean, not good, I think I definitely did better this time, that last time for sure. 'Cause
How long
last
do they take
time-
their scores?
Last time it took like 2-3 weeks. It wasn't, and then they just put on,
Like,
the
maybe
college
like-
board.
Whatever it is.
Oh, was it actually?
mine took 2
Takes like so long.
I don't
He's
know.
like, I think I might have done my SAT like right before, or I got my PSAT like right before my SAT.
Over a month.
It's probably a long communication.
And
That's
okay, so they're not just like.
They're not in a hurry.
Look at so subjective. Have a good one, Shaggy.
You too, thank you.
It's 10 points now, and it's completely different criteria.
No way.
What, what?
You too, thank you.